Okay, guys, so welcome to the next lecture. And in the previous lecture, we looked at continuous functions. F from a metric space X into a metric space Y. And I hope, let me adjust this thing a little bit. Okay, so I don't know what I'm doing, but something isn't working right. Uh, okay, this is better, right? So we're looking at continuous functions from a metric space X into a metric space Y. And remember the definition. I'm not going to repeat it now. I will repeat it later on in this lecture. But the theorems that we proved, which is very important theorem in analysis as well as in topology, that the function f from x into y is continuous if and only if for every open set v in y, the inverse image of this set, f minus 1 of v. So remember, this is a set of all x and x, such that f of x is in v, is open. Okay. So that was, I think, the last big theorem that we proved in the last lecture. Incidentally, this theorem immediately implies the next theorem, that f from x to y is continuous if and only if for every inverse image of every closed set E, for every closed set E in Y is closed. Well, the proof of it is straightforward from the previous theorem. Remember that if E is closed, then E complement is open. Since F is continuous, that means that F minus 1 of E complement is open. All right. So what is it? This is the set of all x and x such that f of x is not in E, and it's open, and therefore the complement to the set so the complement to the set is a set of all x such that f of x is in E. This set is open, and therefore this set is closed. And in that way, open and closed sets somehow completely characterized the notion of continuity of a function. Now, one more remark about it is that for some interesting reason, we do not deal with direct images of this function. We only deal with inverse images of this function. And for direct images of this function, nothing could be closer to the truth, further from the truth. So for instance, if I take a function f that maps real numbers into real numbers, and f of x equals to, I don't know, say 1, all right, in that case, R is an open set in R, but f of R, so the direct image consists of one point, which is one which is not open in R, in a second R. This is the second arrow over here. Okay, so notice that the continuity of a function tells you almost nothing about direct images of open and closed sets, but it tells you everything about inverse images of open and closed sets. And that's kind of the story. And what this lecture is about is how dramatically situation changes if instead of closed or open domain, we will look at X being compact. Okay, and in this case, we're going to prove a theorem in a minute that if f is a continuous function uh, from x to y, remember x doesn't have to be really the whole metric space, it could be just the domain of the function. It doesn't matter, that's the beauty of applying metric spaces. That implies that the direct image of f of x is compact. So again, the story here is that if the function is continuous and the inverse image of an open set is open, the inverse image of a closed set is closed, the direct image of open set is not necessarily open, and the direct image of a closed set is not necessarily closed. However, everything changes if X is compact. So let's try to prove that theorem, and the proof I think is not very difficult if you remember the material from chapter 2 about compactness. So once again, the theorem I'm proving here is that f from x to y is a continuous function if x is compact, then f of x is compact. Okay, so here's a proof, and the proof, in my opinion, is beautiful. It's tricky, but it's not difficult. So I want to prove that f of x is compact. What does it mean? It means that I'm going to cover this f of x by a family of open sets, G sub alpha. So these G sub alphas are open sets in Y. And if I can find a finite subcollection of this set that covers the whole set, then that shows that f of x is compact. So each G sub alpha is open here, and that means that f minus 1 of G sub alpha, this is an open set in X. Agree? Now, notice that this collection of open sets are open sets in X, and X is compact. So what does that mean? That means that X itself belongs to f minus 1 of G sub alpha 1 union with so on f minus 1 of G sub alpha n or G sub alpha n union, etc. In other words, X is in the union of f minus 1 of G sub alpha over all alpha, right? Because every X in X uh, goes into some set in its range, and that means that X is a subset of the union of f minus 1 of G sub alpha. Now, X is compact, and this implies that there exists a finite subcollection G sub alpha 1, etc., G sub alpha n, such that X belongs to the union of f minus 1 of G sub alpha 1, f minus 1 of G sub alpha. Do you agree with me? In other words, every x in X is in one of those things. Good? So if I take an x in X and I look at f of x, that means that f of x is in one of those sets. Let's suppose that f of x is in f minus 1 g sub alpha k. So f of x is in one of those sets, and that means that the range of f of x, this is the set of f of x for all x and x, that this belongs to the union of g sub alpha 1, g sub alpha n. Okay, so once again, what are we doing? We started out with an open cover in y for f of x for the range of the function f, and we found out that the range of the function f belongs to the finite union of that open cover, and that means that the range of f of x is compact. Now notice that this does not mean that y is compact. Y may not be compact. But the range of f of x as a subset of y is compact. Okay, so for instance, if I take the function f of x equals to x squared, and this function will map an interval 0, 1 into the real numbers, then 0, 1, interval 0, 1 is a compact set, and therefore, or let me do it with 0, 2, just for fun. And therefore, the range f of the interval 0, 2, which is actually equal to 0, 4, it is compact in R. Okay, so again, the range metric space, the Y, doesn't have to be necessarily compact, but f of x, the range of a continuous function in a compact set, is compact. This theorem is very, very important for many, many reasons, and many of those reasons you have used in Calculus 1 without knowing that you use compactness. So let's deal with those Calculus 1 problems, and I will start with the definition. A function f from x into, say, R is called bounded if there exists an m greater than 0 such that f of x is less or equal than m for all x and x. Okay, so what's the point of all this? I'm trying to adjust the focus, and I don't know how I'm doing. Okay, so the point of all this is that if x is compact, that implies that f of x is compact. And in particular, if f of x is in R, so this is the case when my function maps x into R. If f of x is in R, that means that f of x is closed and bounded because the subsets of R are compact if and only if the closed is bounded. And in particular, this implies that the function f of x is bounded. Now, furthermore, if I will look at this function f of x, and I will look at since f of x is bounded, it means that I have a supremum over all x and x of f of x, and that will be a finite number because the values of f of x is bounded. This is less or equal than m, and the infinitum of f of x over all x and x is greater or equal than minus m. Okay, so the supremum and the infimum of these functions are bounded. Now notice that f of x is not just bounded, but it's also closed and compact. And if it's compact, it contains all of its limit points. So m and minus, or whatever, the supremum of f of x and the infimum of f of x are, of course, the limit points of f of x, right? Because, for instance, let's suppose that the supremum of f of x is equal to, oh, I don't know, a, right? What does that mean? That means that there exists uh, a sequence of points xn such that f of xn converges to a. But that means that a is a limit point of this f of x over here. And if it's a limit point of f of x and f of x is compact, it means that the limit point is actually belong to f of x. In other words, this supremum is in reality the maximum of f of x. And so the conclusion is that continuous function f from x into R attains its maximum and minimum. Okay, so what I would like you to do next is to think a little bit back into what you did in calculus 1 when they ask you to find the maximum and the minimum of a function f. And remember, the function f was always defined on a closed interval ab. That was, for some strange reason, the absolutely necessary condition to make sure that f has a maximum and minimum on this interval. And it is true that it has a maximum and minimum of this interval, but not because this interval is closed, but because this interval AB is compact in R. And so what you were using is this theorem above that says that f of AB is compact and therefore attains its maximum and minimum. Okay. And that's something that you have been told to use when you were in Calculus 1, but you were never told why. And now you know the secret that this is really the reason why the interval had to be closed. Okay, let's do one more thing about these compact sets. Well, we'll do many more things, but at the moment I'm going to try to do one more thing. And let's suppose that I have a function f that maps x into y. Let's suppose that this function f is 1 to 1 and onto. Well, in that case, again, I'm trying to adjust the focus here. Okay. In that case, this function f, as you know, is invertible. And the inverse is a function from y to x. And there is a very, very natural question to be asked. If f is continuous, does that imply that f minus 1 is continuous? Okay. In other words, is it true that an inverse function of a continuous function is necessarily continuous? And the answer is no, in general. But of course, it is true. I will go to a counterexample later on, but of course it is true if X is compact. Well, why is it true if X is compact? Because if X is compact, it means that f of x, which is equal to y, is also compact. Agree? So f minus 1 of y, which is equal to x, is compact. Well, moreover, if you take any, say, closed subset E in Y, E is closed. You remember the theorem that says that closed subset of compact sets are compact, so E is compact. Now, since f is continuous, it means that inverse image of E, and this is the same as actually applying inverse function to E, that this is closed and therefore compact in X. So what we're showing is that f minus 1 of E for every E closed in Y is closed in X. And by the theorem that this lecture was started with, that implies that uh, the function f minus 1. So, okay, so what's f minus 1 of f minus 1? F minus 1 minus 1 of a compact set, I don't know, R in X is compact. So the inverse image of this function of f minus 1 minus 1 of every closed set R. So if R is closed, R is compact, and therefore this is compact, and therefore closed. And so with that in mind, we obtain the fact that the inverse function of a continuous function on a compact set is itself continuous. Okay, so let's deal with this last part, and I will do the same thing as Rudin does. I will try to give you an example of a continuous function that maps some set x in the metric space y. So in this case, x is not going to be compact. My function f will be 1 to 1 and onto, and yet f minus 1, which exists because every 1 to 1 and onto function is invertible, is not continuous. Now, again, I'm going to follow basically Rudin here. Oh, I don't know what's going on with this focusing thing. Somehow when I move away, then it's focused. If I come close, then it's not, and I don't know what to do with it. So in order to give me an example, I have to do something which in this particular course is illegal. I'm going to refer to the function cosine x and sine x. And of course, in this course, we haven't introduced this function sine x and cosine x. And so basically speaking, I'm not allowed to refer to them, but take it for granted that this particular function cosine x and sine x are continuous function, and I'm going to take x to be a half-open interval. So this will be the interval from 0 to 2 pi, right? It's a 0 is in x and 2 pi is not. And I'm going to look at the function f of t, which is equal to pair cosine t sine t. Uh, and this for 0 less or equals than t less than 2 pi. Okay, so what am I doing here? I'm taking an interval 0 to pi here, and my function f maps it into what? Well, it maps it into two-dimensional space. The space has two coordinates, and if I take any particular t between 0 and 2 pi, then cosine t and sine t are points in a unit circle. So what do the points look like? For instance, if t is equal to 0, then the point here will be 1, cosine of 0 is 1, and sine of t is equal to 0. Then if it goes to be 2 pi, then I will go like this, and I will go like this, and I will go like this, and I will go like this. Now, 2 pi is not included in here. However, at 2 pi, I will have this point 1 back in it. So the function kind of goes all the way to the point 1, but doesn't quite hit the point 1, but the point 1 was there at the very, very beginning. Okay, so is this function one-to-one? Well, yes, because cosine t, sine t is a one-to-one and onto mapping onto this unit circle over here. So you agree with me that this function is one-to-one, and you agree with me that this function is onto. Therefore, it is invertible. So f minus 1 will take this circle over here, and this point 1 is very, very important, and it's going to map it into an interval 0 to pi. Okay, so what is going to happen now? If I take, oops, this should be an open interval, that's the whole point. If I take a point very, 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 very close to 2 pi, so if I take a point somewhere right here, right, then this is the way the function does it, then f minus 1 of this particular point, very, very, very close to this point 1, 0, let's suppose this point is xn, f of xn will be equal to something like 2 pi minus 1 over n, right? So it goes all the way here. And what that means is that if xn converges to 1, then f minus 1 of xn, well, it converges to what? F minus 1 of xn is not going to converge to 2 pi because it should converge to 2 pi, but it cannot because it's not in the range of the function. So the conclusion is that while xn converges to 1, f of xn converges, f minus 1 of xn, sorry, does not converge to anything. It does not converge to 2 pi because 2 pi is not the point in my interval 0 to pi. And so the conclusion is that while this is a perfectly, perfectly good function from this interval 0 to pi, half open interval, into the unit circle, it's one-to-one and onto, the inverse function exists, but the inverse function is not continuous. And so once again, compactness is actually a panacea of many, 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 many difficulties that people have with continuous functions. Okay, so I will end this first part of the lecture on this note. And this should tell you that somehow continuity, while it is a wonderful notion and it relates to open and closed set in a way of inverse images, on compact set, it has all these properties that you had been used uh, to in Calculus 1. And the reason that you always were asked to find the maximum and minimum of a continuous function on a closed interval is because this closed interval is compact, and so the sup and inf exist, and the continuous functions have the properties that if they're invertible, the inverses are also continuous. Okay, when I will return, I will talk about one more property of continuous functions on compact sets, and that will finish this particular section.